message. I'll start by reminding us of what high-dimensional expanders are. Then I'll talk about one application. So let me even do it. Start by some kind of a fast intro to high-dimensional expanders. And we had two definitions. So we gave two definitions for high-dimensional expanders. One was like a global definition through random walks. And the other was more of a local definition through links. And I'll remind what these are. And we saw that they're equivalent, and I want to go again over at least one direction of this equivalence. And then, so that was all of last week's talk. And then there are a few applications that we know so far for these things. And the first one that I wanted to discuss was the mixing of certain Markov chains.
Irit, just checking one thing.
Yeah.
Did you tell Dario it's okay to record? Or?
Yeah, it's Sam up here, and yeah, we talked.
Okay,
so
great.
Hopefully, yeah, maybe it's being recorded.
All right.
So yeah, so the first application is mixing of Markov chains. So we've been hearing about these talks for the last couple of years. It's been very exciting, and even this year at the IIS, we heard several talks, and I wanted to connect these things and show how, from the point of view of high-dimensional expanders, you can kind of immediately get to this result, and you don't need all these beautiful connections that have been or are being made to other areas. So it's just one narrow path to this, but I think it's very simple and very nice. So I want to do that. And the topic that I wanted to get into more today, I'll just maybe introduce a little bit today and then continue next week for those of us who want to keep going. So I would also talk about high-dimensional expanders in PCPs and something that we call agreement testing. And it's nice that for those of you who attended Mark's talk yesterday, he talked about parallel repetition, and so I'll try to connect it to that. It's kind of a nice way to explain what this is and how PCPs want to use these parallel repetition and agreement testing. So that's my plan for today. Okay, so let's start by reminding the two definitions of high-dimensional expanders. So so since I have some people here who weren't here last time, let me go a little bit slowly, but I won't go into all the details that we went through last time. A high-dimensional expander is like we're thinking of expansion, but not in a graph, but rather in a hypergraph. And instead of a hypergraph, we will look at a simplicial complex. This is just like a hypergraph, except you close it downward. So instead of having a hyper edge that contains, suppose, these are vertices, and suppose I have a hyper edge containing these three vertices. Instead of that, I also add these three edges, this edge, and this edge, so that I have it downward closed. So let me erase this. Okay, so this is my model hypergraph, and I have here vertices A, B, C, D, E, F. And we talked about all kinds of random walks that you can do on this simplicial complex. And basically, we look at layers. We had the layer of the vertices. So this is one layer. And then we had the layer of the edges. This is another layer. Was there a question or? Okay. And then we had the layer of the triangles. In this case, in this example, we only have one dimension above edges. So we have vertices, edges, and triangles. So in this, when I say layer, I mean that I put a node here for each one of the triangles. So maybe I overdid it. There's only 3 triangles here. and there's 1, 2, 3, 4, 5, 6, 7, 8 edges. So I put a node here, and there's 1, 2, 3, 4, 5, 6 vertices. And then you connect them through adjacency. A vertex is connected to the edge that contains it, so it can be connected to a few, and an edge is connected to the triangles that contain it. And you can talk about random walks, and you can think of them both on the simplicial complex. You walk from, say, the edge AB, so maybe I can use this. You walk from the edge AB through the triangle to the edge BC. And then you walk from the edge BC through this triangle to the edge BD. And you can also see it on the multi-layered graph where you start from an edge AB, so it's some node here. Maybe let's look at this one. And then you go to a triangle, say the triangle ABC, and from the triangle ABC, you go back to some other edge. So you can look at this random walk here on a bipartite representation, or you can think of it as a random walk on the simplicial complex. And we discussed that there's, I guess, just a moment. So we discussed that, for example, for the layer of the edges, there's two especially interesting random walks. One of them is the random walk that goes from an edge to a vertex to another edge. So this one, if you look at it on the multi-layer representation, it's always walking on the layer of the edges, but it goes from an edge down to a vertex and back up to another edge. And there's another random walk. So this random walk, you first go down and then you go up. So let's call it the lower random walk. And we call it, it really decomposes to two operators, the D operator that goes from an edge to a vertex, and then the U operator that goes from a vertex back to an edge. So this we called it UD. You pronounce it UD, but really it's first the D and then the U. And we also had the upper random walk. The upper random walk, again, is on the same layer of the edges. I'm using this as an example. You can have it on any layer. If you have D dimensions, then you can have it on any layer I that is not the top layer and it's not the most bottom layer. So here on the layer of the edges, you can start from an edge AB, and then you go to a triangle that contains it. So the edge AB is only contained in one triangle, but if I started from BC, then I would have the option of going to ABC or the option of going to BCD, okay? So I start from this edge and I go either here or here. And then once I'm in a triangle, I can go down to one of the three edges that are contained in the triangle. So my movement is an upper one, from an edge to a triangle to an edge. Okay. But in the upper random walk, you could describe it as first going up and then going down. Of course, this is the up. This operator is the one that goes from layer 1 to layer 2, whereas this operator is the one that goes from layer 0 to layer 1. So they are different operators, but they use the same letter. Let me list this. So the upper random walk, I could consider this one, the DU, that goes up and then down. But this one has some laziness factor. The laziness factor is that if I go from an edge to a triangle, and then I go back down, the triangle only has 3 edges contained in it. So there's probability 1/3 that I go back to where I started from. So if we want to factor this laziness out, we use a different operator, which is the L+. And the relationship between these two things is that DU equals 1/3 times the identity plus 2/3 times L plus. So it's just factoring the random walk to the non-lazy part. So this is the
1/3, right? Irit.
say again. Oh,
1/3.
yeah. Thanks. 1/3. This is the non-lazy or non-backtracking random walk. Okay. So, okay, so you can also have in mind that this is just an example with 3 layers, but you can have D layers. And at layer I, you have sets of size I plus 1. You can either go 1 down and then back up, or you can go 1 up and back down. But when you go up and back down, if you have a set of size I, you go up to a set of size I plus 1, there's still probability non-negligible, like probability of 1 over I plus 1 that you go back to where you came from. So you need to factor that out. Or at least we consider the walk that factors this out, we call it L plus. And we sometimes can write the index I to indicate that we're talking about a walk at level I. Okay, so there's some noise. Okay.
I think you should mute everybody.
Yeah, I don't know if I can do it. Maybe Sam can do it. Okay, now it's fine. Okay, so so far I just kind of discussed these 2 kinds of random walks, the upper and the lower, and the definition for a high-dimensional expander just said we want to have for every pair of layers, for every layer, sorry, we want to have L plus the upper random walk and the lower random walk, the down-up random walk, to be very similar to each other in spectral norm. Okay, this was our definition. So maybe I should use more words. So let me move it and say a simplicial complex X is a gamma, a random walk, a high-dimensional expander if for every, let me just see if I can change this, seamless, okay. If for every layer I, this one, when I talk about the ith layer, and here also I'm talking about the ith layer, for every I, you have the upper walk and the lower walk very similar to each other. So this is our definition. And when I say X, so a simplicial complex S is just a collection of subsets that's downwards closed. And the picture I have in mind is this this kind of thing. This is X. Okay. So yeah. Okay. Does anyone have any question about the definition or? Yeah. Okay. So by the way, this kind of definition, the way I wrote it, this is a 2-sided. This is what we call 2-sided. I'll tell you in a minute why it's called 2-sided. And there's also a 1-sided version, which is you just write L plus minus UD is less than, this is like the identity times gamma. So, okay, so this is, if you look at the matrix, these are all, you think of them as matrices, then this notation just says that there's an upper bound on the spectrum. So it's an upper bound, it's from one side. And whereas this guy is both upper bounding and lower bounding the spectrum of this L plus minus UD. So in the one-sided definition, you can have, for example, bipartite graphs that are very good expanders. They can have a negative eigenvalue of -1, so it's not bounded. These are all, by the way, normalized eigenvalues of the random walks. So you can have a negative eigenvalue of -1, but it's still a very good one-sided expander. The two-sided expander, all the eigenvalues that are not the trivial constant one, all of them are very close to 0 between gamma and minus gamma. And we discussed how this definition, so I'm not going to repeat it here, maybe this definition looks very different from how you define expanders, but really this just coincides with the definition of an expander graph. So this completely coincides with definition of spectral expansion in graphs, where in this layer view, where we look at several layers, let me go back. You see here the vertices. You also add a dummy layer. This is like the empty set layer. This is just the empty set, and you connect it here to all of them. And then the lower random walk just goes from a vertex through here to any other vertex. So it's just like choosing, this random walk is basically choosing the next neighbor independently from whatever was before. This is one random walk. And the other random walk is going from a vertex to an edge that contains it to another vertex in that edge. Now you can, with probability half return or with probability half go to the neighbor. After we factor out the laziness, what you get here is just the normal random walk on the graph. So what the definition is saying is that the normal random walk on the graph is similar in spectral norm to the random walk that just goes from vertex to vertex, like on the complete graph. And this indeed, saying that these two are spectrally close is exactly saying something about the eigenvalues of the graph. So this is just a normal definition. So what we are doing in this random walk definition is generalizing it to higher dimensions in this way that seems strange because it's always comparing two random walks inside your own complex. And we discussed that actually that's a very good way to do it, because what would be another alternative? Another alternative people usually like is to have some gold standard object like the complete graph. And you can also have the gold standard object for simplicial complexes can be the complete complex. For example, the graph that has all edges, and then you put in all triangles and all sets of size 4 and so on. And you could presumably say, let's compare this gold standard object to our object. And if they are similar in spectral norm, we will say that, that this is a good expander. But the problem is that our complex might have much fewer edges than the complete complex. Maybe our complex is sparse, so there's only a number of edges that's linear in the number of vertices. And now I want to say something about the random walk going from an edge to a triangle to another edge. How am I going to compare it to the random walk on the complete complex? Even the number of edges that you're walking on is different. So you won't be able, I don't know how to do this comparison. So the way we get around it in this kind of definition is by saying, let's compare the random walk on the edges that goes through the triangles to the random walk on edges that goes through the vertices. And okay, so we make this definition. It's one generalization of high dimensional expanders, of expanders in graphs to high dimensions. But what's nice is that we saw the following claim. We saw that the lambda, the second eigenvalue of this kind of random walk, if you have a high dimensional expander, so let me write, if X is a gamma random walk HDX, then its spectral behavior, the kind of mixing that you see for its different random walks, is the same up to this error of gamma as the spectral behavior of these walks in the complete complex. So you do the definition without reference to the complete complex, but you get as a bonus a behavior that is just like the complete complex. So it's showing you that indeed this definition allows you to look at your object as if it's imitating the complete complex. And the statement is that lambda 2 of the, say, any one of these random walks, but let me just say UDI. So this notation, I just mean the down, up, random walk on layer I. The second eigenvalue of this random walk is I over I plus 1 plus some O of gamma. It's really I times gamma. And maybe I think there might be better estimates, but this is what we proved last time. So what's nice about this is that this is just like the gold standard. If you look at the complex that has all possible I sets of size I of some n element vertex set, and you move from a set of size I plus 1 to I plus 2 and back to I plus 1, you will have exactly this kind of spectral gap. Maybe I'm shifting the indices by 1, but I think this is, I did this before the talk, and this is what I calculated. Okay, so this was the link definition, the random walk definition, and now I want to move to the link definition. So let's see, yeah, how to do it. Okay, so now I want to move to the link expansion. So the nice thing about this definition is very local. It looks at a vertex, and it looks just at the neighborhood of the vertex. And it says if there is some property of the neighborhood, then I will say that this graph is a high-dimensional expander. And this is the definition that's very useful for Markov chains, as we will see, because sometimes, and in this case, it happens to be the case, it's very easy. You can look at the links, and very easily you can see that, the link is a very good expander. And this immediately means, through the theorem that we will go over, you prove that your thing is a link expander. Then there is a theorem that's actually not hard at all, we will see, that implies it's also a random walk expander. These things are equivalent. And then it means to you that the random walk converges. So what is the link expander? So remember we had this definition of a link. So I had this complex, A, B, C, D, E, F. And what is, just to remind ourselves, what is a link? So what is the link? Let's look in this example. What is the link of C? So I look at C, I look at all the neighbors of C. So I guess maybe I should use a thicker pen. Okay. So I look at all the neighbors of C. It's these. So the link of C consists of 3 vertices, A, B, and D. And it's not only the vertices, it's also the edges between them. So if ABC was a triangle, then the edge AB is present in the link. In fact, the link contains all the subsets that contain C after you remove C from them. Okay, so since AC was a subset, when I removed C from it, I get A. That's how I get all the vertices. And then I also look at all the triangles that contain C. So these are ABC and BCD. And I remove C from them. So I get the edge AB and the edge BD. So the link of C is just the graph ABD. This is the graph. This is the link of C. Let's look at another example here. This is the link of D. So the link of D, again, I need to look at the neighbors of D. So it's B, C, and E, F. So the link of D has 4 vertices. And these vertices are also connected by some edges because there is a triangle BCD, so I get the edge BC. There is a triangle DEF, so I get the edge EF. So the link of D looks like this. There's 4 vertices, B, C, E, F, and I have these 2 edges. So this is the link of D. Notice that this link is a disconnected graph. So even though if you look at this fish, it's a connected graph, at one level above it's disconnected, and we see that you already see it in the link of D. Okay, so what was our definition of link HDX? Definition: X, let's say a simplicial complex. X is a link, let's say gamma link HDX, if for every, okay, so if I am in dimension 2, meaning I only have vertices, edges, and triangles, it's enough for me to say for every vertex. But if I want to make a definition that's also relevant for higher dimensions, I need to say, instead of for every vertex, I need to say every I face, meaning every subset of dimension I. But let's start with for every vertex. For every vertex, the link, for every vertex V, the link of V, okay, so the link of V, if V is a vertex and we are in 2 dimensions, then the link of V is just a graph. And then I can talk about the spectral expansion of this graph, because this is a 1-dimensional thing and it's well defined. So the link of V is a spectral expander, but in more generality, I want to say that the link of V, instead of that, I want to say the graph underlying the link of V. The link of V can have higher dimensions. I can always just look at the edges and vertices of that link. And then I want to say that for every I face, the graph underlying the link of this I face is itself a gamma spectral expander graph. Okay, so that was the definition. Just says you look at the face, you look at all the faces containing it, but you remove these elements, you get some other simplicial complex. Now you forget about the higher faces, you only look at the vertices and the edges, and you see if this is an expander. Now you could wonder about this definition. What does it mean to be an expander if your graph is sparse? The whole link is only a constant size, and we said that this is still meaningful because if you talk about the random walk definition, everything is normalized, and there's a difference between spectral gap of 0.9 and 0.1. So this will be actually especially meaningful when gamma is small, like less than 1/2. So think of this as small. Okay. So this was the link definition. Okay, any questions so far? Okay, so the claim that we made last time is that both definitions are equivalent. So maybe before I even continue to that, I want to make some remark that Avi also was making last time I gave this talk, is that this is only one kind of area of high dimensional expansion that is being studied. There are many different aspects of high-dimensional expanders and different definitions. So unlike for graphs, where all definitions are qualitatively similar or equivalent, in high-dimensional expansion, if you take some definition of graph expansion and generalize it, you might end up with very different definitions, and they are non-equivalent. So these two definitions, the link expansion and random walk expansion, are two that are equivalent. But another one that has gotten a lot of interest and I think is very interesting is something called co-boundary expander or co-systolic expansion. These are similar but slightly different. I'm not talking about them at all today, just so you know that these definitions are different and they're more topological, and so they capture different aspects of expansion than the ones I'm talking about today. Anyway, now I want to talk about the fact that these two definitions are equivalent. So really what I know how to prove is that this is true in the two-sided case. And in the one-sided case, we know that the link definition implies the random walk definition in the one-sided case. Anyway, this is the direction, this implication from link to random walk is the implication that is useful for the mixing of Markov chains. There you are interested in some random walk and you want to know if it's mixing, and to analyze it, you look at the link. Okay, so now let me revisit this proof. I want to give the proof again, and because I felt I didn't do it slowly enough. So how do these things relate? The link definition is very local. It's saying at every point, you look only at a vertex and what's going on above it, and you're saying something about the expansion. In the random walk definition, you're talking about a random walk on an entire complex. So how are the two things related? The thing is that when you look at the upper walk and the lower walk, they're always, you can always kind of sort of couple them according to some V downstairs. So let's look at the edge walk, okay? If you walk from an edge, let's say, I'm thinking about some vertex V, and I have a vertex V, and I look at all of its neighbors. Yeah, so I look at the link of this V, and these are, so this is like, I'm thinking of this as being a graph whose vertices are the neighbors of V, okay? And it's not only a graph, right? There's also some edges here, right? So this is an edge, this is an edge, this is an edge, and so on. Okay, so this being an edge means that this was a triangle. Okay, so when I look at the random walk that moves from between two edges through a triangle, maybe this random walk moves from this edge, the edge, oh, maybe I write letters. So this is U, and this is W, this vertex, and this vertex. So maybe this random walk moves from the edge UV through the triangle VW to another edge WV. Okay, so I have this this picture in my mind that I have the edge UV and I have the edge WV. And the reason the upper walk moved between them was because there was a triangle UVW. Okay, so the upper walk moved from UV to UVW to WV. But when you move from two edges, because they're connected by a triangle, they also must intersect on a vertex, right? Two edges cannot be in the same triangle without also intersecting. So there's always gonna be this part too. Whenever you make a move in the upper walk from an edge to an edge, this move is also a legal move in the lower walk. You can also have moved from UV to WV through the vertex V. Okay, so from the point of view of V, when it's looking at some move that happens in its link, this move could have also happened if it was in the lower walk. Okay, so the way we can connect the global random walk definition and the link definition is by looking at the random walk and kind of looking at its different components according to the different V's. Okay, so for every V, you look at what's going on in the random walk above it. And you separate the complete random walk according to these small components. So maybe it's good to understand that from the point of view of V, suppose in my picture here, let's see, make it even bigger. Suppose in my picture here, the purple edges are the only ones that are present, okay? So now in the lower random walk, this move is also legal because you can go from the edge UV, this, to the edge ZV. I don't know, maybe this guy is called Z. Because I'm always allowed, I'm going from the edge to the vertex V and then to another neighbor. So I'm always allowed. So this red edge is allowed in the lower random walk, but it's not allowed in the upper random walk. The upper random walk, only the edges that correspond to triangles are allowed. Okay, so now let's see how, so all this discussion was supposed to give us some intuition. Now let's see how the proof works. So our goal, we want to prove that, goal is to prove that L plus minus UD is less than gamma. Okay, gamma times identity. Okay. So we are assume we have a complex, X is a gamma link expander, high dimensional expander. Okay. So now what does it mean that I want to prove such an inequality? I take, and so I'm focusing on some layer, say it's the layer I. So this operator L plus is operating on the layer I. And I'm not going to prove it in general, just for edges. Okay, so I here, I is one. I is one, we're working on edges. So I take any function on the edges. Okay, so for any f from the edges to the real numbers, I need to prove that f inner product L plus f minus f inner product UDF. So this is an operator that works on functions on the edges. And also this is an operator that works on function on the edges. So writing this makes sense. And I want to show that these two inner products are always less than gamma. This is my goal. Okay. And so I just open it up and I see that what is the first term? This is equal to the expectation of taking two edges, E1 and E2, and writing f of E1 times f of E2. But here, E1 and E2 are sampled according to L plus. So E1 and E2 are a pair of edges that make up a legal step in the L plus random walk. Basically, it means they participate in the same triangle together. Okay.
Irit, gamma should be, I think, multiplied by norm of f squared.
Thank you. Yes. Thanks. And the other expectation, it's the same thing exactly, but now E1 and E2 are chosen not from L plus, but from UD. So basically, in our case, here they're contained in triangle, and here they intersect in a vertex. So you should only think of this as some kind of proxy, because really you need to pay attention to the probabilities, right? So it's a distribution that corresponds to this random walk, where E1 goes to a triangle and then to E2, and in the UD case, E1 goes to a vertex and then to another edge. Okay, and we want to compare these two things. And now we're going to use this coupling and say, oh, let's look at these two expectations by first choosing V at random and then choosing E1 and E2. Notice that in both cases we can do it, right? Because they intersect in the second case, they intersect in a vertex, so we can first choose this vertex and then choose E1 and E2. And when they're contained in a triangle, in particular, they intersect in a vertex. So again, we can choose this vertex and then choose E1 and E2. So we write it like this, please. Choose the vertex and then choose E1 and E2 conditioned on the vertex in L plus. And the same thing. And here, so let's do the conditioning on the vertex. We'll actually do once, and then inside we once write it with L plus, and once we write it with UD. Okay, so far it's just changing the way I write it, but it's equal. These two things are equal. But now let's look at what we have. Let me even copy, so I shouldn't be lazy. Let me copy F of E1, F of E2. And maybe even instead of calling them E1 and E2, let me call them UV and WV. And here also F of UV and F of WV. Whereas here, so what's going on here? Here U and V, sorry, here U and W are not just two random neighbors of V, but rather UVW is itself a triangle. And here, U and W are just the neighbors of V. That's the difference. Okay. So now let's just look at it from the point of view of the link of V. Okay. Let's define GV to be a function from the vertices in the link of V to the real numbers by just saying GV at point U is FUV. Okay, so now we had a function on the edges, but now if we look at the link, we get just a function on the vertices. This function is GV. And now what happens here is that you get expectation over V of the expectation over U, W. This is an edge in the link of V, of GU, GW. And on the other side, we have U and W, just random elements in the link, random elements in the link. And again, GU, GW. Okay, but now let's look at this, this second guy. It's really, okay, this is a trick I can play here that I don't have the ability to do on the board. I can move this like this. Okay, and now here, look at this inner expectation. This is exactly what's measured by the spectral gap, right? Because this is just the quadratic form of the random walk on the link. Here, do you see it? And here I'm just shifting by the expectation. What is this? This is just equal to the expectation of GU on any U in the link squared, right? Because U and W are independent. So I guess I should have written GV everywhere. Okay, so this is just the expectation. You're shifting by the expectation squared. So it's like you took some G that's orthogonal to the all ones after this shift. And you just get that this is always smaller than, the inner part is smaller than the norm squared of GV times gamma. So it's smaller than the expectation over V of GV squared times gamma. And where did I get this gamma? This is what I got from the link expansion. Okay, so the link expansion exactly tells me that locally, the expectation when you go along an edge is very similar to the expectation when you go between two independent vertices. That's what it means for the link itself to be a nice expander. It's exactly the definition. So, and this is what I want because this is the norm of F squared. Yeah, please. Good. So that's it for the proof. So now we have seen how the link expansion implies the random walk expansion. So do you have any? If you have any questions, please.
Irit, just in terms of the intuition of this proof, I mean, you already said that you already made the definition of the random walk expansion for the complex itself, and you can define it for any link when you do include the vertex, right? It's another complex of the same type, right? For every vertex, if you do include the vertex and not just its neighbors,
Okay.
it's also a complex of the same type. And for that complex, the random walk definition and the link, the random walk expansion and the link expansion coincide. And so that's one fact, which you proved there at the very end, because
okay.
it's down, up, and up, down on this link. And the big random walk is just the average of the smaller random walk, the local random walk.
Right.
So that's one. So the link definition is not so that different. It's just the same random walk definition restricted to the vertex and its link, to the complex of the vertex and its link. And
right. I guess maybe the bigger point is that you can write the global random walk as an average of a lot of small random walks. It's somehow you can't always do that, but here you can do.
That's the proof here.
Yeah.
That's the proof here. It's an average of small random walks on the same type of complexes, and right. I mean that's the proof here.
Right. That's exactly this factorization of taking expectation over V, and you get the same object. This is exactly what the proof is doing.
Yeah, I know, but the point I was trying to make is that it seems that the link definition is a definition of the expansion or the normal expansion of a graph, which is a link. But it's also the random walk definition on the complex, which is the link plus the vertex generating it. So it's also
if you want to be precise, I mean the random walk definition goes on all levels, whereas the link definition you always only look at the edges and you forget about everything about
for this edge, for the proof you gave. Yeah.
It's a definition. It's not only the proof, right?
Yeah. No, I'm saying is something trivial. The definition of link expansion is referring to a graph. In the case of, let's say two-dimensional complex with only triangles, it's the same as saying that this smaller complex is a random walk expander, right?
Yeah.
And random walk, the big random walk is just an average of the smaller random walks.
Exactly.
Okay.
Yeah, that's all there is. You see,
Yeah.
it's a very simple. It's more like once you understand what's going on, it proves itself, right? It's not there's no trick. Okay. Okay, maybe just moving to the Markov chains. Should we take a break and return at 11:30? Yeah, let's do that. Okay, so let's take a 5-minute break and continue at 11:30. You have it now?
Yeah.
Okay, good. Break is over. Okay, good. So yeah, so just to reiterate Avi's nice point, is saying what we saw really is a local to global connection, showing that the global random walk definition is equivalent to the local random walk definition. So he's saying you should view the definition of link expansion really as saying a local part of your complex where you just look at the vertex and all of its neighbors and just kind of separate that out and think of it as one complex. This is a small complex, and you were saying, I want this complex to have good random walk expansion. That's the local definition, because you're saying it separately for every vertex. And the global definition is you're looking at the entire random walk. And what we're saying is that these two definitions are equivalent. Okay, so we saw that.
Irit, just a small question. Can you hint at how to prove the other direction?
Yeah.
Because
so,
this seems easier, like more natural.
Yeah, this seems easier. The other direction seems, at first it's like, how can you prove you have some average case assumption? How can you prove a for all conclusion? Because it looks like the global random walk is an average case thing, whereas the local random walk says for every vertex you need expansion. But really, when you have a bound on the spectral norm, you're saying, I know that this is small. What does it mean? It means that for every f, this the norm of L plus minus UD of f is itself small, right? It's smaller than the norm of f. This is what it means. This is what this definition means. So now you can choose your f's carefully. Basically, for every link, you choose f that is supported only on this link. Okay.
Oh, okay, I see.
And then you can prove it. Okay, so it's not really as strong as it sounds. I mean, anyway, this is how you prove it. Okay. Now let's move to the application to mixing of random walks on mixing of Markov chains. So there was this breakthrough result by Anari, Liu, Oveskaran. I didn't check how to write his name, and Vincent, that proved something that was open for many years about the mixing of random walks on matroids. So I don't want to go into all this. I'm also not an expert in this area, but there are many situations where you have some Markov chain on an exponentially large state space, and you want to sample a random element in this Markov chain. And the way, one way that has been very successful is to take some kind of, to construct some kind of Markov chain where you walk from state to state. And if you prove that your Markov chain mixes quickly, then after taking polynomially many steps in this exponential space, you will reach a point that is close to being uniform. And for example, you can want to find a random assignment for some constraint satisfaction problem, or you can want to find a random coloring of some graph. In the case, the example that I want to use today is, or you can want to find a random basis for a matroid, but I don't want to define what a matroid is and so on. So instead, let me just talk about spanning trees. Okay, so what is this is the example. But it's just to talk about something concretely. This actually holds in the same way to any matroid. Okay, so what are we doing? We have some graph. So we have some graph. It's not high dimensional. It's just a bunch of vertices and edges. And we want to find a random spanning tree in this graph. So suppose it's connected. So it has a spanning tree. So it's easy to find one spanning tree by doing one of the algorithms that you know. But there are many different spanning trees. And how are you going to find a typical one, a random one? Okay. Why do people want to find typical ones? Well, it depends. Sometimes you have some other property and you want to measure what is the frequency. So you want to sample a random, say, spanning tree and then check if it has the property, and you do it several times, and that's how you can approximate the frequency of your property. So this is related to things called approximate counting, and not going to talk about it at all, but just to tell you that people are interested in this kind of thing in various situations. So let's go back to spanning trees. How are we going to sample a random spanning tree? So here's an idea that if you think of it for a few minutes, you will think maybe we should try this. You start with some arbitrary spanning tree, and then you modify it randomly. How would you modify a spanning tree randomly? Maybe you remove an edge. Now you get it's disconnected. And now you add some edge that makes it into a spanning tree again. And then you've moved to a new spanning tree. Maybe you can repeat this more and more and keep going. And what you have here is a Markov chain. And the question is, does this mix? Does it mix rapidly? Okay, and this Markov chain is exactly the one we will discuss. So what I want to show you is that this Markov chain indeed mixes, and what these people proved. So the theorem of Nari, Liu, Weizmann, and Vincent is that the Markov chain. Okay, sorry. So let's move this down. The Markov chain of moving from a, so in general, it's for any matroid, moving from matroid basis to another by first remove element and then at random, and then add element at random. So I guess this is sometimes called the Glauber dynamics. So what they proved is that this Markov chain mixes rapidly. So this is their theorem, and I want to prove this. But as I said, I will prove it for the case of spanning trees. Okay, actually, okay, let me remove this comment. So how will I prove it? So step one, we will construct.
What does exactly mixes rapidly means? Like, is there any quantification? Or?
Thank you. Yeah. So let's say in polynomial time. Polytime. So I didn't state what a matroid is and so on, but suppose your universe, your ground set has size n. So it's polynomial time in the ground set, in the size of a ground set. If you're thinking of spanning trees in a graph, then the size of the graph is the number of edges plus vertices. And you want to mix rapidly in polynomial time in that. So even though there might be exponentially many spanning trees, think, for example, of the complete graph. Okay, there's exponentially many spanning trees, right? But So maybe the complete graph is also not a good example because it obviously mixes maybe, but you want to find a typical spanning tree in polynomial time in the size of the graph. Okay, does this make sense?
Yeah, it makes sense.
Okay, good. So, sorry. So the first step will be to construct some simplicial complex. Whose down-up walk, so the lower walk is exactly our desired Markov chain. And the second thing is we will prove that prove it is an gamma HDX with actually it will be with gamma equals 0, which is kind of weird. So it will be with gamma equals 0, but it will be one-sided. So it's maybe remove the word but. It will be gamma equals 0, one-sided HDX through the local definition via the link expansion definition. So we will look at the links of this complex. And this will imply that the entire random walk mixes. Okay. So I will go into a bit more details later on 2, but let's begin with 1. Okay. So what is the simplicial complex? Okay. So now let's do this. So fix a graph. Okay, so the number of vertices in this graph is n, but the number of edges in this graph, let's call it m. Okay, and it can be quadratic in n. Okay, and now we construct a complex whose ground set is the edges. Okay, so construct a simplicial complex X such that X0, this is the ground set. It's the set of vertices of the simplicial complex. So X0 is just E. So it's going to try to not be confused. So X0 has size M. Okay. And now I want to construct a simplicial complex. It will have dimension n-2, meaning the largest subsets will be subsets of size n-1, which are the spanning trees. So let's construct them, start by constructing them. This is just the notation for the layer. So the vertices are the 0th layer, and the edges are the 1 layer, and sets of size n-1 are the n-2 layer. Anyway, what are these? These are all sets of edges that are trees. T is a spanning tree. So for each spanning tree, it's a set of edges. We will put this subset in our simplicial complex, and then we will do a downwards close. So for other layer I, it's just all the sets S of E, such that S has size I-1, and S is contained in T for some T in X n-2.
It's size I+1.
Did I get it wrong? Yes, thank you. Okay. So we constructed the simplicial complex. That was very easy. And now let's look, what does so now we claim that the UD walk on layer, on the top layer, on layer n-2, is the Markov chain we discussed earlier. Right? You start with some element in the topmost layer. Okay, so it's a spanning tree. And then you don't think of it as a spanning tree, you think of it just as a set of edges, okay? A set of elements from your ground set. And now what does the UD random walk do? It says, okay, go down. What does it mean go down? From a set to go down, it just means to erase one of the elements in this set. Okay, so you erase one of the edges. What you get, it's not a spanning tree anymore, it's now a spanning tree that's missing an edge. So it's a forest of two trees. Okay, so now you have this set of size 1 less, and now you need to go up. What does it mean to go up? Well, this forest with 2 components, there might be several different spanning trees that contain it. You can have all the edges that connect between these 2 components are valid. So that would be the spanning tree you go to. Okay, so this is the random walk we wanted. You remove an edge and you add some other edge, and then you remove another edge, you add some other edge, and you keep going. So this is the UD walk. Maybe we should look at an example. I don't know. What do you think? Let's see. Okay, let's do an example. So, example, if suppose G is the complete graph. Okay, so then X0 will have size on, say, on n vertices. Okay, so X0 has size n choose 2, because n choose 2 elements. And what does the random walk look like? So you start, so suppose I have here, I don't know, n is 5. So I have some spanning tree like this. After one step, maybe I can copy it like this. After one step, I erase one of the edges. Okay, erased it. And now I add some other edge. So maybe I add this one. Okay, so that was one step. After I do another step, I erase some other edge. Okay, again. I erase some edge, maybe this one, and I add some other some new edge that's legal. Since I have the complete graph, all the edges are legal, so I add one. Okay, and I keep going like this. Okay, so it should be clear that after polynomially many steps, n log n here, I will converge to a random spanning tree. Okay, so now I want to look and understand the link expansion of this complex X. So what are the links of X? Okay. So we have to fix some set S and look at the links of S. So fix some S in Xi. I is anything, I guess, below n minus 3. You need to go 2 down. And what does the link of a set S look like? So what is S? It's just a collection of edges that is a forest. So it's some collection of edges that has no loops, and you can complete it to a spanning tree. And we want to know who are the elements in the link. Okay, so what does S look like? It looks like some maybe forest like this. So this is S. Okay, so maybe it has even some isolated vertices. So I mean, maybe the graph has some isolated vertices. S is just a collection of edges. Okay, but it won't be nice for me, so erase it. Okay, so this is S, and now what are the vertices? What are the vertices in the link of S? So the vertices in the link of S are all the vertices in the link of S. We're talking about vertices in the complex X. These are elements in the ground set of this complex. So they are really edges of G. Okay. So the vertices in the link of S are some G edges. And which ones are they? So let me tell you which ones they are not. This edge is not there, okay? Because there is no spanning tree that contains S and also contains this edge, okay? So this edge is not one of the vertices in the link of S, okay? But this edge, if it exists in the graph, is actually an edge in the link of S, okay? Also, this edge can be an edge in the link of S, and also this edge. Okay, so basically, the only edges that are allowed are the edges that connect between two connected components. So really what I care about in S is the fact that it is a forest, and it has, in this case, 3 connected components. And then I need to look at all the edges in G that connect between any pair of components. Okay, all these guys, these are the nodes in the link of S. So of course, it depends on the graph G. The size of the link can be large or it can be small. If G was the complete graph, as in our example, then it will be just all possible edges between these components. Okay, so these are just the nodes in the link of S. Now let's look at the edges in the link of S. So an edge, this is now an edge in the complex, so it needs to be a pair of G edges. So an edge in the complex is a pair of G edges. Okay, so it needs to be a pair of G edges that together with S and with this pair, you get a set of size, the size of S plus 2. It should be a set that can be continued to an entire spanning tree. Okay, so I'll tell you which ones cannot be there. This edge cannot be together with this edge. Why not? Because there is no spanning tree that contains the elements of S, so these guys and these guys, plus this edge and this edge, because then there will be a cycle here. Okay, so it's not a spanning tree. So the only kind of edges that are in the link of S are edges that look like this node. Let me do it this way. This node, it looks like an edge because I'm now drawing G, but in the complex, this is just a node and this node. So you're always putting an edge between pairs of nodes that connect two different connected components. Okay, so if I want to now draw this picture from the point of view of the complex, so this is like the point of view in G. And now let's look at it in X, or really the link of S. What does it look like? It has a vertex for every edge in a connected component 1. So let me actually call this connected component. This is 1, this is 2, and this is 3. So, okay, maybe. So this is going to be the nodes that connect 1 and 2. And then I will have also nodes that connect 1 and 3. No, maybe I should do here 1 and 3 and 2 and 3 like this. Okay, so I have here nodes that these nodes correspond to these edges. Okay, these are these nodes. They correspond to these edges. And I also have these nodes. They correspond to these edges. Okay, so far I drew just the nodes in the link of S. Now what about the edges?
You should rotate this picture by 60 degrees and then it will look just like.
Right, thank you. See, it's so nice. Look, da-da-da, like this, yeah? So it's like this, see? Exactly. Wow. This is awesome.
Yeah, fits perfectly.
Okay. Wow. Awesome. Okay. So, right. So now what are the edges? So let's try to take the same color. So the edge from 1, 3 and 1, 2. So I guess I'm connecting this and this, right? This corresponds to this pair. You take an edge connecting 1 and 3, and then you connect it to an edge connecting 1 and 2. Okay, it's not so important. The point is that here I have a complete bipartite graph because I can choose any guy on this side and connect it to any guy on this side. Every pair of these are a legal way to build up a spanning tree. Okay, so maybe it came out ugly, but the point is here that this is really a complete graph. Complete. And similarly, this is complete. Complete. And also here. Complete. So all of these guys are complete bipartite graphs. So this is what the link looks like. The link looks like a complete multipartite graph. It has the number of parts depends on the dimension of S, because when you started from a spanning tree and you removed 7 edges, it means you now have 8 connected components. So there's going to be 8 parts, and it's going to be a complete bipartite graph between these 8 parts.
Not eight parts. 8 choose 2 parts.
8 choose 2 parts. Thank you. Yeah. Okay. Thanks. That's right. So I guess for 3, 3 choose 2 is the same as 3 choose 1. But in general, it's true. And you have a complete bipartite graph on this 8 choose 2 parts. What varies from graph to graph is how many edges are in each part. It doesn't only vary from graph to graph, it varies from S to S, depending on which spanning tree you started with, or partial spanning tree you started with. The number of the size of the different components changes, and the number of edges connecting between them changes. But the links always look like this, like a multipartite graph, and it happens to be a fact. So fact for such graphs, lambda 2 is always negative. It's always not non-positive. Okay. And the meaning of this is that immediately means that X is a gamma equals 0 one-sided link expander. So that's it. So once you just kind of carefully look at the links, you see that they have a very, very simple structure. It turns out that their expansion is actually super good. And that's it. And you get your expansion, and from the link expansion, you get the mixing. And just to say, remember, maybe I even have it here in the beginning of the talk, we said that, you see this? So this is the slide from the beginning of the talk. We had this fact that if a graph is in HDX, then we know something about its, not only do we know that the upper walk is the same as the lower walk, we also know something about the spectrum, the spectrum of this walk. And we said it's I over I plus 1. So if in our case I equals n minus 1 or something, because that's the top level, this is the random walk we're interested in, our lambda 2 is I don't know, n minus 1 over n or something like that. I don't know about the shifting one. But anyway, the spectral graph is 1 over n, on the order of 1 over n. And if you're worried about this error term, I mean, you should be, because we didn't do it. These kind of complexes unlike the complexes I talked about until now, I only talked about complexes that had vertices, edges, and triangles. That's it. But really, when we talk about this mixing, the number of dimensions you have is non-constant. You have n minus 1 dimensions. Okay, so you might worry about the constant here in the accumulation, but we actually showed in the proof that you get here some constant times I times gamma. Maybe even the constant was 1. So if gamma is 0, then this term just vanishes. And you get here that the lambda 2 is at most I over I plus 1. In the case that we need, it's n minus 1 over n. Okay? So you get the spectral gap of 1 over n. What does it mean you have a random walk whose spectral gap is 1 over n? It means that after you do n log n steps, you mix. Or anyway, polynomial in n, you mix very well. So that's, I think that completes this, this part. Okay, so the UD has spectral gap 1 over n, meaning that lambda 2 is less than 1 minus 1 over n. And so mixes in time poly n. Great. Okay, so that's, I think that's all I had to say about this. So yeah, any questions? Okay, so what do you think should we, I mean, I'm a bit hesitant about continuing to the second topic, given that it's already 12. Let me.
Can I ask a small question?
Yes, yes, please.
So what, you tried this, it's amazing, but have you, like,
Yeah.
what happens if you tried to do this for something like matchings?
Oh, I don't know. Okay, let's see. So let me say one thing where there's a significant trouble that comes up, and this has to do with the weights. So far, I completely cheated. I didn't talk about weights at all. And this was okay because in what I talked about before, I talked about the Markov chains. And I told you that introducing the weights is easy and it's just technical, so it's not a real cheating. Here, you need to take care of the weights, but in the case of the matroids, actually, it works out. So what am I talking about with weights? When you talk about a simplicial complex and you close it down, you need to not only just combinatorially add the smaller subsets, you also need to think of the smaller subsets as having weights proportional to how many larger subsets contain them. Okay, so for example, when we think of graphs and the graphs are not regular, it's natural to give vertices weight according to the stationary distribution. If a vertex has many neighbors, it has larger weight, and if it has fewer neighbors, it has smaller weight. So if you have more dimensions, you look at all the spanning trees on top. Maybe the graph is such that one edge is used in all the spanning trees, right? The graph can be like a barbell where this edge must always be. So this edge has huge weight. It's contained in all the spanning trees, and other edges have much smaller weight because maybe they're not so important. So when you analyze the spectrum of the links and all these things, you need to analyze the spectrum of the weighted graph that you get from this. Okay, and it turns out that in these cases, it's still true that the graph is a multipartite complete graph, and lambda is always non-positive. So what I said is not incorrect. But for other cases, for example, for colorings, and I don't know what happens for matchings, the weights give you a huge headache, and I don't know necessarily how to analyze it. But anyway, let's just for fun, what is the matching situation? You have a matching, so you can put a top face for all the matchings in a graph, and then your Markov chain kind of erases an edge. I guess I should do. And how do you move from one to the other? It's more complicated, no? Okay, maybe the answer is I don't know, and maybe it's better to think about it offline. But I guess it's not the kind of dynamics that you erase something and add something instead. So
It is the
maybe
same kind. It is the same kind of dynamics exactly, but
yeah. How
it's
is it?
not. But not in a matroid. You just don't have this contraction. I mean, things are not local. In the spanning tree, the example where you had the link, you just basically contracted the connected components and you got another matroid. And this is not true for things that are not matroids.
What's the next step from what I drew? I have a matching missing an edge. Now what do I do?
In this, so I think there you need to define a random walk on nearly perfect matches.
So here is a nearly perfect matching. What do I do now?
No. Then you go down and then you go up. What you do in the
Maybe you need to remove two steps. You do like this.
Yeah, that's what you do there.
If you can. It's not always clear you can do
No,
that.
exactly, if you can. But,
you look at the ones available to you.
Yeah.
Yeah, so
this in the here and in colorings and in all of them, they are all very local random walks, but you don't have this ability to contract, which you do in the case of matroids. Right? There's no notion of contraction. So you don't reduce, when you fix some subset to be in your family, it's not true that you can just contract it and get a similar structure. In matroids, it's true. And that's how you got this complete bipartite graph.
Just a short comment that matching is intersection of two matroids. So this is the more general case.
Yeah, but it doesn't help, so it doesn't help that it's an intersection of two matroids. It's true, but it's, there are lots of situations where you don't have a matroid and at least this analysis fails. You may or may not be able to do something, but this analysis failed. There was a lecture a few weeks ago in the seminar where, it was talking about colorings, for example, and there you can do something, but it's more complicated. And it's not.
I was talking about independent sets. I think the colorings case is still open, actually.
It depends for what. It depends for what gap between. How many colors you allow relative to.
Right. If you.
Yeah.
Right. So maybe Fotis can say something. I'm really not an expert on this. I guess maybe what is the point of this is just that it happened to be, maybe it's a coincidence, that the matroids case was still open, and when you look at the link of these things, they happen to be very easy multipartite graphs, and so this connection kind of made this work. But you see that the proof actually it's some inductive thing. I think it's a good way to it's a good tool to have in mind that you can move to the links and analyze, but sometimes the links are more complicated. In the case of coloring, really the difficulty is the weights. I don't know what else to say. Any more questions? Okay, so let me, I feel it's not a good idea to start a new topic. So I just want to tell you that, like as a promo for next week. So I got interested in these objects because they seem to be very relevant to PCPs. And specifically to something called agreement tests. So yesterday, Mark showed us a new result relating hardness amplification from MaxCut to two unique games. And what he showed was that you have some graph, it's the odd cycle graph in their case, and you can define a two-player game on this graph that whose value is like the max cut value. And then you do something that is parallel repetition. We call it parallel repetition, which gives you a unique games instance. And the point of the unique games instance is that now the gap, some kind of hardness got amplified. Without getting into details, I'll do it more carefully next week. But really, what is this parallel repetition transformation? In fact, they were even talking about symmetric parallel repetition. What is this parallel repetition transformation? It's really saying, look, in the game, instead of asking one player one vertex and the other player another vertex, I'm going to ask one player a set of vertices, okay? Some k vertices, and I'm going to ask the other player another k vertices. Okay, so if I think of it abstractly, I had some graph G. And initially I had some game that involves just two vertices in G, but now I have a game that involves a whole subset of vertices in G that I ask the first player, and maybe another subset of vertices of G that I ask the second player. Okay, and I can look at the collection of subsets as a collection of faces in a simplicial complex, and look at some kind of a random walk that goes from S to S prime. Okay, and it turns out that the cases that we know how to analyze correspond to where this collection of subsets are some kind of high-dimensional expander. Okay, so I'm really not saying a lot about this. Yeah, so actually, yeah, I feel like maybe it's too much to start this now. So maybe I got tired. So so next week I want to describe this kind of questions and this whole direction of you know, getting stronger PCPs by various kinds of amplifications. Even the basic PCP theorem is an amplification statement. You start with something with very small gap and you slowly amplify it. And kind of a very simple method for amplifying is through moving from a question about one vertex to a question about a bunch of vertices, like we have in parallel repetition. And you can study this by looking at the combinatorial structure of this as a simplicial complex or a high-dimensional expander. So yeah, we'll talk about this maybe next time. Okay, so I think that's it for now.
Okay, we'll thank Irit. If there are any more questions? All right.
Thank you.
Okay.